Good morning. Okay, so let's continue on with chapter 7, which is, it's a big chapter. There's definitely a lot in it. Let me look at the syllabus real quick. So, oh, good thing we did. Yeah. Okay. So we're supposed to be done with chapter 7 today. I'm not sure if that'll happen. We'll see. If not, I'll push the homework out. And then next week, we don't have class on Tuesday. Tuesday is a professional development day. So that means I have work, but you guys don't have class. So enjoy. As far as the end of the week, nuclear chemistry, we may get to nuclear chemistry or may end up having to just pack in chapter 7 there. But nuclear chemistry is kind of a quick chapter, so I'm not concerned about that. So yes, so don't meet on Tuesday. So I will see you a week from today as far as class is concerned. Okay, so we had talked about calculating the molar mass for a molecule or a compound, right? So you need to add all the individual molar masses together. You have to multiply it by however many of them you have, right? So if you've got 2 carbons like we had in this, you need to multiply the molar mass times 2. If you only had 1 carbon, you'd only multiply it by 1, right? So that does have an effect. These are what some mole quantities of different things look like. So here's a mole of sulfur, here's a mole of iron. And remember, each one of these things is how many atoms and or molecules. Each one of these contains 6.022 times 10 to the 23rd of the individual amount. But you can see that the volume of it gets bigger as we move to the right. Why is that the case? Because you have more atoms within that given molecule. But in general, when we're talking about a mole, it's like a human scale amount, okay? So 1 mole of anything, you could hold it in your hand. Sometimes when we extrapolate that out to 6.02 times 10 to the 23rd atoms, it's like, what does that even mean? It's something that you could hold in your hand, all right? So if we've got a molar mass of a, what do you call it? Oh, my brain is just not there today. If you have the molar mass of a compound, like we have methane here, we can convert between mass and moles and mass. I don't want to do, let's see. Yeah, I guess we can actually do that. Okay, so calculating moles from mass or mass from moles, same thing that we did with the individual atoms, or I'm sorry, with the individual elements. So state the given and needed quantities, write a plan to convert. You have to calculate the molar mass for any sort of compound and then convert. So let's do this one here. A box of table salt, NaCl, contains 737 grams of NaCl. I want you to tell me how many moles of NaCl are in that box. So you're going from grams to moles. I'll give you all 2 minutes for that one. Okay, so in this problem, we're given grams and we want to calculate the moles. So going from grams to moles or moles to grams, we need a molar mass. And in this case, we need a molar mass of NaCl. So we would need to take the mass of one sodium and add it to the mass of one chlorine. So the mass of that should be 58.44, right? One sodium is 22.99. One chlorine is, oh, that doesn't look right. This is not 38.45. This is 35.45. Still adds up to the correct amount. That's a typo right there. Okay, the molar mass of chlorine though is 35.45. So we've got these two different conversion factors or molar masses. Which one do we want to use? Well, if we're going from grams and we want to get moles, that means grams need to be on the bottom and moles needs to be on the top. So we would use this second one. When we set it up in our dimensional analysis, we always start with our given information. So 737 grams of NaCl. We will multiply it by, and really we divide it by the molar mass, right? We're putting the gram value on the bottom and the mole on the top. The grams will cancel and we'll be left with a value of moles, roughly 12.6 moles of NaCl. Now, remember the one goes with the mole, the number goes with the gram. I see that happen all the time where someone will go, oh, 1 gram of NaCl is equal to 58.44 moles. That is definitely not the case. So just make sure you keep those where they need to be. Let's do another one. So a sample of water has a mass of 59.8 grams. How many moles of water are in the sample? So if that first one was a little rocky, hopefully this one will feel a little bit easier. It's very similar to the last one. We just have different values. Setup is the same though. Okay, so we know how much water we have as a mass, 59.8 grams. How many moles of water are in the sample? So we want to go, I'm going to draw it out. Given 59.8 grams, we're trying to find moles. And this is specifically of water. Water is H2O. That is one of the very few, I think the only compound that I expect you to know the common name. Okay, so you need to know water is H2O. So in order to go from grams to moles or moles to grams, if we're going from grams of H2O into moles of H2O, the relationship we need is the molar mass of H2O. So it's 2 hydrogens and 1 oxygen. It's roughly 18 grams of H2O for every 1 mole of H2O. So we start with our given. We have 59.8 grams of water. And if I want to get moles, well, 1 mole of H2O is always going to be equivalent to roughly 18 grams of H2O. All right, so I think the slides use 18.02. I can add that. The grams will cancel and we'll be left with moles. So 3.32 moles of H2O. So if it's a compound, you have to do the extra step of calculating the molar mass, right? If it's an element, you just get to look at the periodic chart. If it's a compound, you've got to add that extra little bit. So looking at this all smushed together, I do just love this flow chart. So I'm going to keep this up and we're going to have a little bit of fun with this. So I'm going to give you something and you're going to have to find something. You're going to need to figure out where are you starting and where are you ending. It's probably going to be multi-step, okay? So given you have 21.6 grams of aluminum oxide. I want you to find number of oxygen atoms. Okay, so 21.6 grams of aluminum oxide. Find number of oxygen atoms. So looking at this, we're starting with aluminum oxide. That's a compound and gram is a mass value. So we're going to go to mass. We're starting over here. Number of oxygen atoms, that's a particle, and specifically atoms, we're going to end over here. So you've got a couple steps to take. You can go a few different ways. You can go here and up. You can go here and over. I will give you 5 minutes to get that set up. And calculated, sorry. Set up and calculated. Okay, so the thing that's nice about this flow chart is that if you know where you're starting and you know where you're ending, you just sort of follow the system and it tells you how to hop from each step. Let's move out of this for a sec. Okay, we're given 21.6 grams oxide. We're trying to find number of oxygen atoms. So off of that flow chart, what we should do is we should start with grams of aluminum oxide, and you have to figure out what the formula for aluminum oxide is. So it's Al2O3. Can't get that, you can't calculate the correct molar mass. So grams of aluminum oxide, and then that's going to go into moles of aluminum oxide. And then from that, I can go, looking at our chart over here, grams into moles, then I can go moles of element and then atoms of element. You could go molecules and then atoms either way, but I'm going to go this way. So then we get moles of oxygen. And then we get number of oxygen atoms. Now, as far as filling in these steps, I mean, it tells you here what you need. You need the molar mass of the compound, you need the formula units, and you need Avogadro's number. So here we need the molar mass of aluminum oxide. $101.96. So I'm just going to fill in my details here. So 1 mole of Al2O3 is equivalent to 101.96 grams of the Al2O3. That goes there. This here is the relationship between the number of oxygens within each mole of the compound. So 1 mole of Al2O3 gives you 3 moles of oxygen because the subscript 3. And then here, this is 1 mole of anything. In this case, we're looking at oxygen. So 1 mole of oxygen is equivalent to 6.022 times 10 to the 23rd oxygen atoms. Again, you're going to see me add a 2 there, an additional 2, because I'm teaching other classes. We usually use 1 additional 1. If you use just the 6.02, you'll be fine. So we have to start with our given, which was what, 21.6 grams. So 21.6 grams of aluminum oxide, Al2O3. We're going to first get that into moles. So if I want moles, the mole needs to go on top. 1 mole of Al2O3 on top for every 101.96 grams of Al2O3. Then, you could stop and solve, but I'm going to just chain them together. If I want to go from moles of my compound, 1 mole of Al2O3 into moles of oxygen, well, we get 3 moles of oxygen. So it's a 3-to-1 ratio. In the next step, for every 1 mole of oxygen, we get 6.02 times 10 to the 23rd oxygen atoms. So don't really think about or stress about, like, am I multiplying or dividing? I just set it up so everything cancels. So gram of compound cancels with gram of compound. Mole of compound cancels with mole of compound. Mole of element, in this case, oxygen, cancels with mole of oxygen. And we're left with just the oxygen atoms, which is, at the end of the day, what we wanted. And let me plug that in real quick. 21.6 multiply across everything on top. So times 3 times 6.02 to the 23rd. And then we need to divide it by the molar mass of 101.96. And we end up with a very large number, I'm going to use 3 sig figs, so 3.83 times 10 to the 23rd oxygen atoms. Does a really big number make sense? Totally, because we're dealing with oxygen atoms. So we wouldn't want that to be anything teeny tiny. Okay, you got to let me know if you have any questions with that or with that setup or how to read the flow chart. You can put it in the comments or you can take your mute off real quick and I can try and I can help you. If not, I'm going to assume that you are good to go with that. As far as understanding it, you will have to definitely do more practice on your own. Okay. So again, this is very, very useful whenever you're taking, doing homework or taking an exam or anything like this. I would have this available to you so you can just, where am I starting, where am I ending, and then follow the flow chart. So the second part of this chapter is talking about chemical equations and chemical reactions. And we're going to, again, we will eventually tie it back into moles and molar mass and all that stuff. But for now, let's talk about what it means to have a chemical change, because a chemical reaction is an equation that expresses some sort of chemical change. And a chemical change is when a substance is converted into one or more new materials. So you're starting with something and what you're ending with is not just like a different phase. We're not just melting it. We're actually like inserting atoms or breaking atoms off, things like that. So a tarnished fork is a great example of a chemical change. In the beginning, we're starting with just pure silver, but this is very reactive to oxygen in the air. So, well, in this case, it's sulfur, it's reactive to sulfur. So it will grab sulfur from its surrounding areas and make a new material. The tarnished stuff on top is Ag2S or silver sulfide. So the new thing actually has atoms packed away in it that were not there in the original structure. So here's another example. This is like a fresh set of nails that are made out of iron, and they will rust. The rust goes through is a process of oxidation, so it does actually pull oxygen out of the air and give you that rusty quality. A chemical change occurs when a substance is converted into one or more new things. You know, our eyes aren't sensitive enough to see the change happening. Like we can't actually see, you know, little baby oxygen atoms getting inserted in with the iron because it's too small. But we can see secondary effects or macroscopic effects. So a lot of times chemical changes will be associated with bubbling, a change in color. Color is not always the case, but sometimes if you see this change in color, it can indicate chemical change. Production of a solid. So if I have two liquids and all of a sudden, boom, a solid pops out when I mix them together, that's probably indicative of chemical change. And then anytime we see heat being produced, so it gets hot to the touch or it gets cold to the touch, and I'm not talking you put it in the fridge and it gets cold, talking about it sitting on the countertop and you're mixing two things together and they get cold. That's a indicator of chemical change. Also, if light is produced, it's a good indicator of chemical change. So when we are talking about a chemical change, we need to be able to express it. And so the way that we express it is in this thing called a chemical equation. Just like, you know, elements, you can kind of think of elements as the letters and compounds as the words, and the chemical equation is the sentence. Okay, so now we're taking our words, our different elements and or compounds, and we're mixing and matching them together in an equation that expresses some sort of change. So here I've got carbon and it's reacting with oxygen. So we're pretty much burning the carbon in this case. And on the left side of this equation, these are known as your reactants. You need a minimum of one. but you can have many more than one. In this case, we have two different reactants. They're separated by a plus. Right? So we have carbon plus oxygen. On the right-hand side are your products. Again, you have to have a minimum of one product, otherwise it's not a chemical reaction, nothing has happened. But you can have many more than one. In this case, our product is CO2, so they're burning carbon and they're getting CO2. In between the reactants of the products, it's separated by this arrow. The arrow is what's saying, hey, we've changed into something new. We've gone through a chemical shift. This little delta here is letting me know that heat was produced in this process. You will also see that there are little italicized letters in parentheses. Those are phases. So not always are chemical equations do you give the phase, but a lot of times you may see it. So what this is saying is it's not just carbon, but it's actually solid carbon is mixing with gaseous oxygen to produce gaseous CO2. So it's not giving off dry ice, it's giving off carbon dioxide as a gas. So to write a chemical equation, an arrow needs to separate your reactants, what you're starting with, from your products. Reactants are written on the left, products are written on the right. We separate multiple reactants and or multiple products by a plus sign. Delta sign in this case lets us know that there's heat being produced. And then we add the little physical states to denote what phase we're in. So S is for solid, L is for liquid, G is for gas. And then a new one that you may not be so comfortable with is AQ. That means aqueous. So that just means that you're presenting the, because so many reactions, especially reactions that happen on Earth, are happening in water situations, we give it its own phase. But that just means that you're delivering the material dissolved in water. So if I say NaCl solid versus NaCl aqueous, this is saying I'm actually putting solid a solid like table salt into the reaction. Here I'm saying that the salt is being dissolved in water and then presenting in the equation dissolved. So there's a bunch of symbols that you may see. You have the arrow with the little delta. That's indicating the reactants are heated. You can sometimes see other things above this, like PT, which is for platinum, or nickel. Sometimes those are, we use those as catalysts to help propel the equation forward. But for now, just the delta symbol should be enough for you. So when we are looking at this equation here, this one is already balanced. And when I say balanced, I mean that it is honoring the law of conservation of mass. And the law of conservation of mass says that in any chemical reaction, the mass you start with has to equal the mass that you end with. So when we're dealing with chemical reactions, and now this is going to be different in the next chapter when we do nuclear equations, but for anything chemical based, the number of atoms that you start with of each thing needs to equal the number of atoms that you end with. So in this case, I have 1 carbon and 2 oxygens. At the ending situation, I have also 1 carbon and 2 oxygens. So reactant atoms equal product atoms. So this one just happens to already be balanced for us. That's not always the case though. Sometimes equations aren't balanced, and so we need to balance them. So in order to balance an equation, first you need to write the equation using the correct formulas. So you can't change subscripts. Sometimes people will go, oh, well, you know, let's say instead of this equation here, I had the equation carbon plus oxygen, O2, produces carbon monoxide, okay? Well, in this case, we're not balanced. Here we have just 1 oxygen. Here we have 2 oxygens. And so sometimes what people want to do is say, oh, well, I'll just put a 2 down here. No, because what we produced was not carbon dioxide. What we produced was, in fact, carbon monoxide. So I can't change subscripts. I can't change what the formula is. I have to honor the fact that it's carbon monoxide. The only way to change the amount is to use these things called coefficients, which we put in the front. So I would put a 2 here, and then I would put a 2 there. Okay. So when it says first step, write an equation using the correct formulas for the reactants and products, it means if it says aluminum oxide, it's got to be Al2O3. You can't do it as AlO. You want to count the numbers of atoms on each side, on the reactant side and the product side. And then we use coefficients. So we use numbers in front, which act as multipliers to balance each element. And then we check to make sure at the end that it is in fact balanced. Again, we don't want to change subscripts. So we've got this thing here. Al plus S gives me Al2S3. So it's saying aluminum plus sulfur gives me aluminum sulfide. I'm going to write that over here. So aluminum plus sulfur gives me aluminum sulfide. There are phases on there. I'm not going to add them. Why is it Al2S3? Well, because anytime aluminum and sulfur come together, that's the formula they're going to produce. Remember, aluminum is a metal with a charge of 3+. Sulfur is a metal with a non-metal with a charge of 2-, flip-flop, Al2S3. So I can't change subscripts. That is what aluminum sulfide is. So when looking at this, first thing we want to do is I like to put all the elements that are present. So I have aluminum and I have sulfur. Then I'm going to count them up. So aluminum on this side, I have 1. Sulfur on this side, I have 1. Aluminum on this side, I have 2. Sulfur on this side, I have 3. So I need to put numbers in front in such a way that it will balance out. This one's pretty easy. Usually you want to balance metals before non-metals. So let's go with aluminum. There's 2 aluminums on this side. I need to get 2 aluminums on this side. So I'm going to put a 2 in front. I would never put a 2 here because aluminum is not a diatomic molecule. It doesn't do that. So instead, I'm going to say I have 2 aluminum atoms. That changes this to 2. Sulfur, there's 3 on this side. So I need to get 3 over here. Again, I'm not going to put a 3 down here. I would put it in front. Look, now we've got 2 on both sides and we have 3 on both sides. This thing is balanced. So these are the correct coefficients. The coefficient that exists here is just an inferred 1. You don't have to write the 1. So going through their slides, they say, you know, as far as aluminum, you have 1 aluminum and 2 aluminums on the product side. 1 starting sulfur, 3 ending sulfurs. I mean, the law of conservation of mass, you can't just create matter out of nowhere. It's not like, or it can't just disappear into nowhere. If I have 1 aluminum atom, I can't all of a sudden just have 2 aluminum atoms. I have to abide by that rule. So they put a 2 and a 3 and it's now balanced. Check and make sure everything works. So again, couple things that help out with balancing. Balance metals before non-metals. Also, if you ever have a free element, so something that exists by itself on one side, balance that at the end, because it usually kind of fixes everything else. So this here, these are already balanced. It says state the number of atoms of each element of the reactant side and the product side. Okay, so here we've got 4 phosphorus, P4, that means there's 4. Here, know that this number gets distributed to everything in there. So I have 4 Ps and 4 Ps. As far as the number of bromines, well, Br2, so there's 2 within the molecule, and I put a 6 in front of it for a total of 12. So I'm gonna put 4 here, 4 here, and there are 12 here. What's going on over here? Bromine has got a subscript of 3, and there's a 4 in front of it. So I multiply my coefficient by my subscript. That would give me 12. Okay, looking over here, aluminum, I've got 2 aluminums, I've got 2 irons, and I've got 3 oxygens. Let's hope that that's the case on the other side. Over here, I've got 2 irons, 2 aluminums, and 3 oxygens. Yes, so we're all balanced. All right, so this here says balance the chemical equation when solid iron oxide, Fe3O4, reacts with hydrogen gas to produce solid iron and water. Oh man, this one's kind of fun. Okay, we're gonna take a break from that for a second because that's kind of adding another layer to what we're doing. I want to just balance some equations. Let's go ahead and balance equations. I'm going to give you, I'll just write a couple over here. So I'm going to give you the skeletal equation. That means I'm going to tell you what the reactants and the products are, and you have to balance it. So the first one, Na combines with Cl2 to produce NaCl. Okay, so you're going to start balancing these. Give us a little more space. 2. I got to come up with some of these. Let's say we've got hydrogen gas plus nitrogen gas to produce ammonia NH3. Let's see. AlBr3 plus K2SO4 produces KBr plus Al2SO4 3. All right, so you work on those 3, counting up the number of atoms you're starting with and you're ending with, and then work to put coefficients to balance. Okay, so we'll go over these. This first one, you know, the types of atoms I have sodium and I have chlorine. I have one sodium on the starting side and I have two chlorines on the starting side. On the end side, I have one sodium and one chlorine. So the sodiums right now are balanced, the chlorines are not. I have two here, so I need to get two over here. Now I can't put a two there because that would make sodium chloride NaCl2, and that's definitely not what the compound is. So instead I need to put a two in front of it. That will change chlorine to two, right? Because this gets distributed out. It'll also change my sodium to two. And sometimes people will get a little freaked out because they're like, oh no, this was balanced and now it's unbalanced. That happens sometimes. Sometimes you'll have things that were working, were parallel, and then they get messed up. And we'll just go ahead and fix that. I can put a two right here, and then that moves to two. This next one here, and I have nitrogens and I have hydrogens. I start with two nitrogens and two hydrogens. I am ending with one nitrogen and three hydrogens. So that's, yeah, those are definitely not balanced. So if I've got two nitrogens here, I need to have two nitrogens over here. So I'm going to put a two here. That changes this to a two. And then it also changes this to a six, which I like this being, right now it's an odd number. I want it to be an even number because look at what hydrogen is over here. It's a diatomic. It's got to be a multiple of two. So if we have three here, I can't put any sort of coefficient in front of here to get to three. But when this gets two'd in front, that turns this to a six. Now I can put a three over here and we are balanced. So the whole goal is to try and get the number of atoms that you're starting with to equal the number of atoms that you're ending with. This last one down here, this one's kind of messy because it has a polyatomic ion in it. But if you notice, the polyatomic ion stays intact, right? It doesn't break up into sulfur and oxygen. It stays SO4 as a packet. So what I'm going to do is treat it as a packet. So I have aluminum, I have bromine, I have potassium, and then I have sulfate, SO4. And I can keep that as a unit because it doesn't, again, change. So aluminum, I start with one aluminum. I end with two aluminums. Here I start with three bromines. I end with one bromine. Here I start with two potassiums. I end with one potassium. And here I start with one sulfate ion. And I end with three sulfate ions. I like this. Like when I'm setting this up, when I'm seeing that there's twos and threes on opposite sides, it means that we're going to have some sort of like common factor of six. So we can start with the metal. If I've got two aluminums on this side, I need two aluminums over here. So I'm going to put a two. That's going to change aluminum to two, but it also has an effect on the bromine, right? We had three bromines. If I two that, that's going to give me six. All right. So then from there, we can balance the bromines. If I've got six bromines here, I need to have six bromines over here. So I'm going to put a six in front of there. That changes bromine to six. And it also changes potassium to six. Okay, and then we can balance the potassiums. If I've got six here and two here, that means I need to put a three in front of there. That changes this to six. And then the three actually gets distributed out to the sulfate as well. And now I have three sulfates. Look, 2, 2, 6, 6, 6, 6, 3, 3. And we are balanced. Done. So practice is going to help a lot. If you go online and look up like balancing chemical equations, you'll get a bunch of them. The homework is going to help you as well. You're not always given things though, like the way I gave it to you, where it gave you the reactants and the products in nice, neat written compounds. Sometimes you have to do that step of writing the chemical formula. So that's what we have going on over here, where we see where it says write a balanced equation with solid iron when it reacts with hydrogen gas to produce, solid Fe3O4 reacts with hydrogen gas to produce solid iron and water. So this is a word problem where we've got to write an equation. So what I like to do is figure out like where the reactants and the products are and separate it out. So it says to produce. So anytime you see the word to produce or to form or decompose or anything that there's some sort of change, that's your arrow. All right, so that is separating the reactants from the products. So where are my reactants? Well, one of the reactants is this thing here. The other is this thing. These are my two reactants. And then my products are what we get formed. So it says we form solid iron and we form water. So let's start by writing our reactants. Well, the first reactant is given to me as Fe3O4, and it says that it's solid, so I'm going to add a little S. This combines with hydrogen gas. Okay, hydrogen gas is H2, diatomic. So when you're doing these word problems, you always want to be asking yourself, is this a diatomic molecule? Because if it's a diatomic molecule, you need a 2. If you don't include the 2, it throws the whole balancing process off. Remember, the diatomic molecules have no fear of ice cold beer: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So don't forget that. And it says that it's a gas, so we'll give it a little G. To produce solid iron. So solid iron is just Fe by itself. So Fe, and it's solid. Is iron a diatomic? No, so it doesn't get a 2. And then we add that to water, which is H2O, and it's a liquid. So this is the skeletal formula. You got to go from here to this. Now we can balance. So what do we have? We have iron, we have oxygen, and we have hydrogen. I have 3 irons starting with. I have 1 iron to end with. I have 4 oxygens to start with. I have 1 oxygen ending, and I have 2 hydrogens over here and 2 hydrogens over here. So I guess, we could balance the iron, but it's kind of, the iron's by itself, so I kind of want to leave that to the end. I'm going to do the oxygen first. So there's 4 over here, and there's only 1 over here, so I'm going to put a 4 in front of there. That's going to change this to 4. It also changes this to 8, okay, because 4 times 2 is 8. So then I need to get 8 hydrogens on this side, so I can put a 4 here. That changes this to 8. And then the last thing is to balance the iron. There's 3 there. I need 3 over here. So we've got a coefficient of 1, 4, 3, and 4. This is obviously much more difficult than if I just give you the compounds. So what do you have to do here? You have to remember your nomenclature. And there we go. There we go. We are done with that. Balancing with polyatomic ions, I kind of already went over this, but if you have a polyatomic ion in there and it stays the same, so the polyatomic that you start with, it stays a polyatomic ion when you end with, because there are some chemical reactions that can actually pull a polyatomic apart, but if the chemical reaction you're dealing with doesn't pull it apart, just treat it as a unit. So like this thing here, sodium phosphate and magnesium chloride, produce magnesium phosphate and sodium chloride. You can see that the phosphate stays the same. Here's the little phosphate, and here's the phosphate. It's just multiplied by 2. So we can treat that as a packet. Count up how many of each thing we have. We have, in this case, 3 sodiums, and then 1 sodium, 1 phosphate, and then 2, 1 magnesium, and 3 magnesiums, and 2 chlorines, and then 1 chlorine. We want to start messing around with them so that we can get the same amount. And in this case, it's a coefficient of 2, 3, and 6, which will balance us out. All right. I want you to mess around with these. I want you to balance A, B, and C. It gives you like the coefficients. You can pick 1, 2, or 3. I don't really care so much of that. I just want you to balance it. Okay. So I'll give you about, let's see what we're sitting at, 8:57. I'll give you 5 minutes to balance those. Okay, so looking at these, your coefficients for this first one, it should be 2, 3, 4, and 3. I want to move forward a little bit just so that we can get everything in by the time we need. So this B, you should have had 2, 3, 3, and 1. And then C, you should have had 2, 3, 1, and 3. If you didn't get those and something was amiss, stay after class and we can go over it individually, but I want to move forward. Okay, so we need to talk about the different types of chemical reactions that we can have. So there's a bunch of different types, but there's some main ones that we see sort of happen over and over again. The first, one second. We can see them here. So we've got combination reactions, decomposition reactions, single replacement, double replacement, and combustion reactions. A combination reaction, these are all examples of combination reactions. So this is where two or more elements form one product. It's a simple compounds combined to form one product as well. So we've got this A and this B, and they come together to form a unit AB. We can also see here, this is that idea of like a simple compound of SO3 and H2O water to give us H2SO4. So A plus B gives us C, combination to combine. We have another type called a decomposition reaction. So to decompose or to break apart. So we start with a substance and it splits into two or more simpler substances. So here we've got HGO, mercury oxide, and it breaks into mercury and oxygen. Or we've got AB and they break up into A and B. Same thing here, I've got potassium chlorate and it breaks up to potassium chloride and oxygen. What you break up into isn't always necessarily a single element. It could be just a simpler substance. So here we've got something that's a little more complicated than this thing here. It's still a compound, it's two things, but it's simpler than the three things we started with. And then there's the oxygen. Here's decomposing mercury 2 oxide. So we've got mercury 2 oxide, and when we decompose it, the mercuries and the oxygens separate and forms a gas. This oxygen is a gas. We've got a thing called single replacement. So a single replacement reaction is when one element takes the place of a different element within a compound. So I've got A and then there's BC. So BC, you can kind of think of this as like the home wrecker situation. So BC are already together, or they're married or whatever, they're a unit. A comes along and looks much more appealing to C than its current partner B. So what C will do is it will kind of push B out and it will take A and we get a new compound. So we can see here's zinc by itself, and then here's the hydrogen and the chlorine. Well, the chlorine decides I would much rather be with the zinc and it pops the hydrogen out. Same thing here, we've got iron and then we've got copper sulfate. The sulfate decides I would much rather hang out with the iron, I'm more attracted to the iron. So it sort of pushes out the copper. Another, this single displacement or single replacement happens all the time. Anytime we dissolve a gas, or I'm sorry, dissolve a metal with acid. So I've got a zinc bar here, and the zinc is dropped into some hydrochloric acid. The hydrochloric acid will, we say quote unquote, eat away at the metal. Well, what's actually happening is that the chlorine from the hydrochloric acid dissolves the zinc, brings it into an aqueous form, and then the reason it's fizzing is because it's giving off hydrogen gas. We have another thing called a double displacement relationship. So this is like a swingers situation where we've got a couple and a couple, or a compound and a compound, and they swap partners. Okay, so usually this is a metal and a non-metal and a metal and a non-metal, and the metal from one will combine with the non-metal from another. So AB and CD become AD and CB. You can see here's the metal on the first, here's the metal on the second. The metal from the first moves to the non-metal of the second. So Ag combines with chlorine, sodium combines with the nitrate. Now, in this situation, you're not going to see a metal combine with a metal. okay, or a non-metal combined with a non-metal. It's always going to be the metal of one with the non-metal of the other, and the metal from the second with the non-metal from the first. Here we've got another one, so the zinc switches spots with the hydrogen. You want to be able to identify these, like when you have a chemical equation, is it a single displacement, double displacement, combination, or decomposition? There's one more called a combustion reaction. So a combustion reaction is going to be anytime you have some sort of carbon containing compound, and that carbon containing compound can have hydrogen. Sometimes it can also have oxygen with it, but we've got some sort of carbon-based thing. It combines or burns with oxygen, and you will always produce CO2, H2O, and energy, okay? It doesn't matter how complicated this hydrocarbon gets. What you're gonna get on the product side is CO2 and H2O. So do know that, okay? Because I could technically say, hey, methane, write a combustion equation for methane. You would have to take the methane, you'd have to combine it with oxygen because it always combines with oxygen, and you're going to produce CO2 and H2O and then balance it out. So here's a list of all the different types of reactions. Really quickly, I want to do one of those combustion reactions. Here we go. Okay, so let's say write a combustion reaction for for ethane. Okay, and you may not know what ethane is, but it's C2H6. So if I write a combustion reaction for this thing, here is my hydrocarbon. So that goes in the first slot, plus the hydrogen gas, or I'm sorry, where is my brain? C2H6, okay? So if it's a combustion, always add oxygen. And oxygen is a diatomic, so I'm going to write it as O2. And my products are always going to be CO2 and H2O. Okay, so like if you know this thing, you can fill in the other ones because you've got it memorized that it's going to combine with oxygen and it's going to produce CO2 and H2O. And then it also produces energy. But we're not so worried about that with balancing. So now we want to balance. We've got carbons, we've got hydrogens, and we've got oxygens. Carbon, I start with 2, I end with 1. Hydrogens, I start with 6, I end with 2. Oxygens, I start with 2, I end with 3, okay? Because there are, you have to add all the oxygens. There's 2 here and there's 1 here. So when I balance the carbons first, so there's 2 here, I'm gonna do 2 here. That changes this to 2. It changes my oxygen to 4, 5. All right, after you balance carbon, balance your hydrogens. That's just a rule of thumb when doing combustion reactions. Do carbon, then hydrogen, then oxygen. So hydrogen, I have 6 over here, and I want to have 6 over here. So I'm going to put a 3 in front of here. That changes this to 6, and it changes oxygen to 4, 7. Okay. So we're balanced except for this right here. If I want to, the fastest way to get that balanced is, well, if I want 7 here and I want to get 7 here, how do I get 7? Well, if I go 7 divided by 2, that would get me 7, right? Because the 7 divided by 2 times 2 would leave me with just 7. 2 times 2, 2 times 1 over 2 gives me whatever just the top value is. We don't like to have halves though. So what I'm gonna do is get rid of this 2 and multiply everything by 2. So I'm gonna multiply this by 2. I'm gonna multiply this by 2, which will just give me 7. I'm gonna multiply this by 2, which will give me 4. And I'm gonna multiply this by 2, which will give me 6. And now we are balanced. It does change all these things. This is 4. Now this is, 12. And this is 14. And we are balanced. So the coefficients would be 2, 7, 4, and 6, and you'd be done. Okay, so we're gonna stop there. I might do another one of these next time. If you have any questions, stay around. Otherwise, enjoy the rest of your day. And I will see you on Thursday because we don't have class on Tuesday. Bye, everybody.